So we briefly reviewed circuits last lesson, so let's have another review of that. And so let's talk about series circuits first. So when we say a circuit is wired in series, it means that the same current goes through each component of the circuit. And the way that that happens is that the circuit has its components located on the same length of wire. And so what we had is an example of resistor 1, resistor 2, and a battery delta V. And we said the following, that the total voltage drop, which is equal to the source voltage, so that's the voltage of the battery, is equal to the current through resistor 1 times the resistance of resistor 1 plus the current through resistor 2 times the current of resistor 2. And we rearrange this to say, well, the current going through the circuit, because it's the same in a series circuit everywhere, is that. And so you just have to add the resistances up and then divide that figure by the voltage. Now, if we took a slightly more complex example, where we have a circuit that's wired in series and in parallel. So let's say we have a 12-volt battery here. We have a resistor 1, and we have resistor 2, resistor 3, resistor 4, and resistor 5. So resistor 2 and 3 are in series, resistor 4 and resistor 5 are also in series, but resistors 2 and 3 are in parallel with 4 and 5. And so let's say that the total current going around this circuit was 2 amps. How would we find the value of this resistance here? So let's think about that. So if we have a circuit, and let's give these easy values. Let's just say this is 2, this is 2, this is 2 ohms, this is 2 ohms, this is 2 ohms, this is also 2 ohms, just for convenience sake. So what we have is resistors in series, which we can combine together. So let's combine resistors 2 and 3. So the total resistance would be 4 ohms of those two, and it'd be 4 ohms of these two. Now, since these ones are in parallel, let's do that. It's going to be the following. We have 1 over 4 plus 1 over 4 equals 1 over the total resistance. So what we've done here is we've combined those resistors 2 and 3 and 4 and 5 into a single resistor. So let's redraw the circuit to make sense of that. So when we combine resistances, we can actually get a new hypothetical circuit. So this is 4 ohms here and 4 ohms here. And we have another resistor, resistor 1. And so we can combine the resistances here, because those ones are in parallel. We use this formula, 1 over resistor 1 plus 1 over resistor 2 is 1 over the resistance total. So let's do this. So we have 2 over 4 is 1 over R. So R is equal to 2. So the total resistance of resistor 2, 3, 4, and 5 is 2 ohms. So let's redraw the circuit one last time. And now what we have is resistor 1 here, and we've combined these resistances to get a new resistor. Let's just draw it as a rectangle. That is 2 ohms. And we have the battery, which we said was 12 volts. So now what we have is a series circuit. And for a series circuit, we said that 12 volts, total voltage, divided by 2 plus resistor 1, so 12 volts over the total resistance, is equal to 2 amps. So 12 volts equals 2 amps, 2 plus R1, and so 12 is equal to 4 plus 2R1, 8 is equal to 2 times R1, so R1 is 4. And so now, what we've done is we've calculated the resistance of resistor 1. So that's kind of where we left off at in terms of resistance. Now there is a formula for resistance, not resistance, but series and parallel circuits, and that's resistance is equal to the resistivity times the length all over the area. Now this is an important formula. So resistivity has the units of ohms per meter. So that's how much resistance per meter. And then length has the units of meters, and then area is the cross-sectional area in meters squared. So when we cancel the units here, what we get is this. Ohms all over meters squared. And so what we have is a formula that links the resistivity with the length and the cross-sectional area. And so this is an important formula to understand, because as the length of a wire goes up, its resistance goes up. As the area goes up, resistance goes down. Now, resistivity is dependent on the material. So, in most cases, you can assume that the resistivity is 0 of a wire if the passage is not stated. But the resistance of silver, for example, is 1.5 times 10 to the minus 8 ohm meters. Sorry, that was my mistake. The units for resistivity are ohms times meters, and then you get meters on the top and meters squared on the bottom. So meters squared will cancel with meters squared, so you get ohms, which does make sense because that's the units of resistance. Sorry about that. Okay, so let's talk about the power. Okay, so power is in joules per second. And the power of a circuit we can calculate as the following. It's the current, which is coulombs per second, times the voltage, which is in joules per coulomb. So we end up getting joules per second. So P is equal to IV. Now, we can make a substitution here, because V is equal to IR. So P is equal to the current multiplied by IR. So current, or I times I, is I squared. So you get I squared R. It's good if you can derive these formulas, because it does add to your understanding. So let me make a circuit, and we can calculate some of these. So we have resistor 1, resistor 2, and we have a 12 volt battery, and resistor 1 is 3 ohms, resistor 2 is 2 ohms. So the current going through the circuit is 12 volts all over 5 ohms. That's 12 over 5, which is 2.4 amps. So we have a 2.4 amps going through the circuit. So P is equal to IV. P is equal to I squared R. Let's compute the power going through the circuit. So we could do 2.4 times 12. And that would give us the following value, which would be 2 times 12 is 24. And then 12 times 0.4 would be 3. So we have 27 joules per second. So let's have a look at some examples of circuits, where we have to calculate some of these values. So R2 and R3 are in parallel, R1 is in series, and we have a source voltage with V. Okay, so rather than use actual numbers, I'm just going to go and basically do it just as the letters, just for time's sake. So what's the current through resistor 1? Pause the video and see if you can find the answer. Okay, so we could redraw this circuit and we can combine resistor 2 and resistor 3. So 1 over R2 plus 1 over R3 is equal to 1 over the resistance total. So if we are to make a common denominator for these, let's just cross multiply. In fact, it might actually just be easier if I give numbers. So I'll give numbers. I'll just say resistor 2 was 2 ohms, this was 3 ohms, and this was 4 ohms. Or, yeah, we could say that. So, let's do this. So, resistors 2 and 3, let's combine them. So it's 1 over 3 plus 1 over 2 is 1 over the total resistance. So let's put them all over 6, since we can just combine these. So we have the following, which would be 1/3, which is 2 over 6, and then 3 over 6, which is 5 over 6, so it's 6 over 5. That would be our total resistance, combining these two resistors. Now 6 over 5 is 1.2 ohms. Next we'll do the new circuit. So we have 1.2 ohms here, we have 4 ohms here, and we have our battery. We can say our battery is 6 volts. And so you can do it from this point in the video, because now all you have is a circuit in which you have two resistors in series with each other. Now, the one thing to know about parallel circuits that I haven't mentioned is that even though the current between two resistors that are in parallel could be different, when the current comes back and rejoins, it will equal the sum of those two currents. So if we had two resistors here, and there was 2 amps going through here and 3 amps going through here, then 5 amps would exit the circuit. So although the current through each resistor is different, the current that exits is not. So that is one thing that I wanted to make clear. So yeah, figure out that current, and then I'll be back with you. Okay, so we had 6 volts, right? And we had 6.2, sorry, we had a total resistance of 5.2. Yep, 5.2 amps, so 6 over 5.2. Now, that is our current that goes through this. So we can go ahead and compute that. So that value is approximately going to be 6 over 5. Now, although that isn't the correct number, for the purposes of the MCAT, we can approximate it that way. So it's unlikely that you'll get numbers like this since I just made them up, but if you want to approximate them, you can do. So I'll just say that's about 6 over 5, which will be about 1.2 amps. So that is the current. Now, if we wanted to figure out, well, what is the power, right? What's the total power of this circuit? Well, if we have 1.2 amps going through the circuit, and we said our battery was 6 volts, it was 1.2 amps multiplied by the voltage, which is 6 volts. So 6 times 1.2 would be our answer. Now, this is not exact because I did do some rounding, but roughly 7.2 joules per second. So the next thing we're going to talk about here is capacitance. So let's talk about capacitance. So a capacitor is a way that you can store charge. So let's have a look at examples of capacitors. So there are things that you know that have capacitors in them. And so a capacitor is something that is going to store charge. So let's think of a common everyday example of a capacitor. So radio receivers use capacitors. There are many other things that actually store electrical energy. What would be another one? Sometimes on circuits they use them to keep things safe and stop them being damaged electrically. So capacitance is the storage of charge, and it's defined as the following. If we have two plates with different charges on them, so we have a battery here, so the positive terminal goes onto this plate, the negative terminal goes onto this plate. So I'll redraw it just to make it proper, but we have one that goes here, one that goes here. You get a positive charge here, and a negative charge here. And what we have in between is an insulator. So an insulator stops the flow of charge, otherwise the charge would just jump to the next plate. And so the capacitance is defined as Q over delta V, which is the capacitance. It's measured in coulombs per volt. So, if we wanted to rearrange this, we did Q times delta V, C times delta V for the capacitance, we get the charge. Now, what if I asked you, if we have two plates parallel to each other, and they're separated 0.02 meters apart, and they're connected to a 6-volt battery. So, we have this scenario. If we wanted to move a charge of 2 times 10 to the minus 14 coulombs from the negative plate to the positive plate, how much work would need to be done? So, we have this thing called an electric field, where we have positive charge here and negative charge here, and they're separated. And we have a distance between them, which is 0.02 meters. And we want to figure out how much work is required to move the charge from the negative to the positive. Now, why is that difficult? Well, this is the electric field. These lines that go from positive to negative, those are the electric field lines. And what you're doing, if you're going in the opposite direction, is you're going in the reverse direction. So you're going against the electric field. So we know that work is in joules. We also know that charge is in coulombs. And we know that voltage is in joules per coulomb. So we can get joules. So work is equal to Q multiplied by delta V. So if we had 2 times 10 to the minus 14 coulombs, and we have a battery which is 6 volts, that's how much work it would take to move it against the electric field. What if we wanted to find the force the charge experiences doing this? So, work is equal to force times d cos theta. And in this case, we want to solve for the force. So, we know that this is our work. We also know the distance that it's going to have to travel. So, what is going to be the work done? So we have 0.02 meters to travel. Sorry, what's going to be the force? So it's 2 times 10 to the minus 14 multiplied by 6 volts divided by the distance times cos theta. Now theta is, in this case, 1. That is because the field is uniform. So we go and plug these numbers in. So we have the distance, which is 0.02 meters. And then we get the work. So this is like an introduction to electric fields and capacitance, and can hopefully help you solve some questions that you get on capacitance. And one thing about circuits is there's a lot of unit conversions. So one thing that you should try and get good at is really figuring out how you can get really fast at those unit conversions. So next, let's think of some problems that we can work on together. So, here we go. So, we have a battery at a certain voltage. Is this following statement true or false? Pause the video and see what you think. So the answer is it's true. The voltage drop across 3 resistors in series is equal to the sum of their individual voltage drops. So delta V of resistor 3 is equal to the current times the resistance of resistor 3. Delta V resistor 2 is the current times the resistance of resistor 2. Delta V resistor 1 is the current times the resistance of resistor 1. These will all add up to the the voltage of the battery. Next question. If I double the current through a circuit, so the current is doubled, how much does the power increase by? So P is equal to I squared R. So if you double the current, the power increases by a factor of 4. So these are just some brief conceptual problems that you can have a think about. So this is all for this lecture on circuits, power and capacitance. It is more on the brief side, but you should do lots of practice for your MCAT exam.